In this video, we're going to look at the behavior of sequences. So a sequence is said to converge if the terms get closer and closer to some value. So if you've got the relationship between the sequences is to get my next term, I multiply the previous term by k. Then the sequence converges if k lies between -1 and 1, or the nicer way of saying that is modulus of k is less than 1. So let's have a look at an example how this might work. So in this example, it says a sequence is defined by the recurrence relation un plus 1. So that's to get your next term. You divide your previous term by 2, and also it tells you your first term is equal to 1. Find the first three terms. So that's dead easy. Your u1 is equal to 1. Your u2 is 1 divided by 2, and your u3 is equal to half divided by 2, which is a quarter. Okay, the next bit, it asks me to find the 15th term. So we're looking for u15. Just going to say that's equal to a question mark. That's what we're trying to find. A wee bit tricky to do this. Okay, we're going to find the nth term of this sequence. So the recurrence relation to do this, if you want to do it by recurrence relation, you could, but that would mean you'd have to divide your quarter by 2, your eighth by 2, your 16th by 2, and so on. Do that until you get to the 15th term. So it's not a very efficient way of doing it. So your nth term, let's say our nth term is going to be it's going to be 2 to the power of minus something, and it's going to be n minus 1. So let's just check that that works. So put in 1. 1 minus 1 is 0. 2 to the power of 0 gives you 1. Put in 2. 2 minus 1 is 1. 2 to the power of minus 1 then is going to be a half. Put in 3. 3 minus 1 is 2, and 2 to the power of minus 2 is a quarter. So you can see it does work, this nth term. Okay, so what we want to find is u15. So it's just a calculator exercise now. u15 is going to be 2 to the power of minus, and then 15 minus 1 is 14. 2 to the power of minus 14. So my u15 is going to be equal to 1 over 16384. Okay, does this sequence converge? So remember we've set up here it converges if your modulus of k is less than 1. So that's what we want. So here we have got, in this example here, k is equal to a half. So that means, so the sequence, that's less than 1, so the sequence converges. Happy days. Okay, so if the opposite of converging is diverging, and it diverges, then if k is greater than 1 or less than minus 1, or else you can say, a better way of saying it is the modulus of k is greater than 1. Okay, how we find the limit of the converging sequence? So if you imagine a sequence converging to 1, it might get the terms, maybe the first term may be like 0.4, and maybe it's 0.7, maybe it then goes up to 0.95, and then maybe goes to 0.97, and so on, 0.99, and so on. It's going to keep going and going. So you can see a sequence like that, it looks like it's getting closer and closer to 1. It sort of got up quite quickly up towards 1, and then it sort of slowed down a wee bit. So it looks like it's going towards 1. That's not a very mathematical way of doing that. So when it gets to its limit, the next term basically is going to be equal to the previous term, and we're going to call that limit L. Okay, so if a sequence is converging towards a limit, we can discover the value of a limit by using the fact that when the sequence reaches the limit, each subsequent term in the sequence will become equal. So after a while, here as I moved along, after a while my terms would just become the same thing. So we're going to look at an example of how this works. Okay, this example we've got a recurrence relation, and it's un plus 1 is equal to 1 plus 1 over un, and this first term of the sequence is 1. Given the fact that the sequence converges, find a value to which the terms converge. I'm going to let my thing converge to L, and I'm going to say let un then equal L, and also un plus 1 equal L. So I'm going to just put them both into this formula and see what happens. So So just say, therefore, L is equal to 1 plus 1 over L, and then we're just going to go with this. You should remember from like solving quadratics down the school, you will have x is equal to 1 over 1 plus x. What you did in these cases, you multiplied through by x to give you x squared is equal to x plus 1, and then you would bring it all to one side to have that equal to 0. So that's what you would do here. Same idea. So we're multiplying everything through by L, so just timesing by L, and I'm going to get L squared is equal to L plus 1. And then bring it all to one side. I'll have L squared minus L minus 1 is equal to 0. Okay, that's not going to factorize nicely for us, so we're going to have to use our quadratic formula. So L is equal to, my B is minus 1, so minus B then would be equal to just 1, and plus or minus 1 squared minus 4 times my A, which is 1, times my C, which is minus 1. Use brackets here again. I think I said this in a previous video, but use brackets, please, just to avoid mistakes. Show you're working out, so on your calculator, work out what is inside that square root. So that's going to be minus 1 squared, which is 1, minus 4 times 1 times minus 1, which will be plus 4, so 1 plus 4. So inside that bracket just works out as root 5. Okay, and your last thing then, so my L is going to be equal to 1 minus root 5 all over 2, or it could have been L is equal to 1 plus root 5 all over 2. Okay, the final answer, however, is L is equal to 1 plus root 5 over 2, which is the positive one. The reason that's the answer is if you think back to the original setup, my initial condition, my first condition was 1. First term, was 1. My second term then would be 1 plus 1 over 1, which is positive. My third one then would be a positive plus 1. My fourth one would be a positive plus 1, and so on. So you'll never get a negative value. So for the limit to be this thing, which was negative, is impossible. So you have to take this as your answer. Okay, this example says a sequence is defined by the recurrence relation. Un plus 1 is equal to 4 un all over 3, and the first term is 1. Find the first three terms of the sequence, and then does the sequence converge? So the first, your u1 is just 1, your u2 is 4 over 3 times u1, which is just 4 over 3, and your u3 is 4 over 3 times 4 over 3, which is 16 over 9, and I'll just leave it as that. Okay, does the sequence converge? Or converge? The sequence diverges. The reason it diverges as k is equal to 4 over 3, therefore k is greater than 1, and that was the conditions for the sequence to diverge. It is possible for both convergent and divergent sequences to both oscillate. So an oscillating sequence is one in which the successive terms are alternately higher and then lower than the previous term. So a very easy oscillating sequence to look at would be minus 1, 1, minus 1, 1, minus 1, and so on. That would just be an oscillating sequence. You could also have other ones, sequence such as 2, minus 4, 8, minus 16, 32, and so on is also an oscillating sequence. Right, we're going to look at an example of this one now and see how it looks. Okay, this example says, by calculating the first 5 terms in each case, state whether the following sequences are convergent or divergent, and whether or not they oscillate. Find the limit L for any convergent sequences. So the first one we have is un is equal to minus 2 to the power of n, so we will look at it now. So un is equal to minus 2 to the power of n. So our u1 then is just going to equal to minus 2 to the power of 1, so just minus 2. Our u2 is going to equal to minus 2 to the power of 2, which is going to be 4. Our u3 is going to equal to minus 2 to the power of 3, so minus 8. And so on. It's going to be 16, and u5 is going to be minus 32. Okay, a good way to do this is to do a little sketch. So this is a very basic sketch. I've just got my ur. So that's my general term and my r. So when r is equal to 1, my term was down here was minus 2. So it's a very, very rough sketch. This is just to get an idea of the shape. When r is equal to 2, it was 4. When r is equal to 3, it was minus 8. When r is equal to 4, it was 16. When r is equal to 5, it was 32. So there we've got our terms. If we just link those up with a wee line, you can see they go very roughly like that, and they're getting more and more spread out. So it is clearly divergent. Okay. Okay, for the next one, for part B, un plus 1 is equal to 6 over 1 plus un, and u1 is equal to 3. So your u1 is equal to 3, we'll just write that down again. u1 equals 3. Your u2, when you put it into this formula, your u2 is going to be 1.5. Your u3, again, put it into the formula, you'll get 2.4. And u4 is going to be 1.76. I've got the 2dp's, and u5 is going to be equal to 2.17. Okay, it seems to be convergent and also oscillating. So it starts at 3, and then it goes to 1.5, and then it goes back up to 2.4, and then it goes to 1.76, and then it goes to 2.17. So it's definitely oscillating about a point, and it looks to me like it's convergent. So it seems to be convergent and oscillating. It seems to be convergent and oscillating. So we're going to have to say let un equal L, and also, most importantly, un plus 1 equal L. So L is equal to 6 over 1 plus L, and then we'll just multiply across, and you're going to get L plus L squared is equal to 6, or L squared plus L minus 6 is equal to 0. And this one factorizes, that's going to be L plus 3 upon L minus 2 is equal to 0. So you've got L plus 3, put that equal to 0, that means L is equal to minus 3, or L is equal to 2. Right, now this is just where it takes a wee bit of common sense. If you look at what we've got, these have never even been negative, and it does look like it's gone from 3 to 1.5, then to 2.4, then to 1.76, then to 2.17. So it definitely looks like it's converging to 2. So you can see our sequence converges to 2. Okay, in this example it says find the first 4 terms of a sequence whose nth term is n minus 1 over n plus 1, and investigate what happens to the nth term of the sequence as n increases. So again, just rattle through your u1 is just going to be 0 over 2, which is just going to be 0. Your u2 is going to be 1/3. Your u3 is going to be 2 over 4, which again is just a half. u4 is going to be equal to 3/5. And your u5 is going to be equal to 4 over 6, which is 2/3. Now, if we have a wee look at this, it does look like it's converging. It looks, we've got 0, we've got 1/3, we've got a half, we've got 3/5, we've got 2/3. It does look like it's getting closer and closer to 1, but we can't really say for sure that that is the case. Let's look at the nth term of this thing and see if we can get any closer to this. So un is equal to n minus 1 over n plus 1. Now I'm going to give you the proper mathematical way of doing this, and then another way which really works just as well, but it's not what they would want in the exam, but it would test it for you so that you know you're on the right track. Right, we're going to say as n, and what this line means, that means as n tends to infinity. So as n gets incredibly close to infinity, what happens is your un becomes infinity minus 1 all over infinity plus 1. So that means, therefore, your un tends to, okay, right, now if you've got infinity minus 1 is basically infinity. infinity plus 1 is basically infinity as well. So you've got infinity divided by infinity. So the same thing divided by the same thing. So it's just going to 1. So what we've said here basically, we can skip this middle bit out. As n tends to infinity, un tends to 1. So that basically means if you go all the way along to as far as you can go, your term becomes 1. Okay, right, I just finish this off. How would finish? We would say, therefore, just say, so the sequence converges to 1. Okay, right, I'm just going to show you another way of doing this, and I'll be taking this out of your notes. So this really is just it's not the proper way of doing it really, but it works. Okay, another way you could do this is just put in a very, very big number. So we're going to look at our un, and we're just going to put in 1 million. So if you have a 1 million, so 1 with our 6 zeros, 1, 2, 3, 4, yep, minus 1, and the bottom line is your million again plus 1. So it's not infinity, so this isn't the good mathematical way of doing it, but it works. So if you've got a million minus 1 on the top line and a million plus 1 on the bottom line, so you do a million minus 1 divided by a million plus 1, you're going to get pretty much 1 if you do that on your calculator. Okay, so that sort of tests this out, because I know this is something a lot of people don't like, so test this thing out, and that's it. Okay, I'll be getting rid of this for your notes. Okay, this next bit we're just going to look at the graphs of sequences. So you can see here, this is a graph of a convergent sequence. You can see as we move along, the terms definitely get closer and closer to 0. So this is called monotonically, means the gradient maintains the same sign. So it's this gradient all the way down is going to be 0. This one is divergent, because as you go along, you can see the terms are getting further and further apart. So this would be like an exponential sequence or whatever. So it's getting further and further apart. Okay, in this one, this is an example of a convergent but oscillating sequence. If I was just to draw in lines between these terms, you can see it would go very, very roughly like this, and it's getting very closer and closer to 0. So it's just oscillating towards a point. This one again, next one is oscillating but divergent. If I was just drawing in lines between these, you'd see they're getting further and further apart. So they're oscillating as well. Oscillating and divergent as well. And the last one here is a sequence which repeats itself with a set number of terms. Is called a periodic sequence. The functions sin x and cos x are examples of periodic sequence. And you can see here we've got the cos graph, and the period is 2 pi. So every 2 pi radians it repeats itself, or that's the same as 360 degrees if you haven't seen your radians yet. So you've got sine, cos, cosec, and sec all have a periods of 2 pi. Some of these graphs you may not have seen just yet, don't worry about them. And your tan graph and your cot graph, your tan graph has a period of pi, so or 180 degrees. So every 180 degrees the tan graph repeats itself. So if they ask you about a periodic sequence, it's just how often does it repeat itself. Okay, you're now ready to do sequence and series exercise 6.